learndeep.ca and hope you all had a great week. So in this class, we'll be learning what is supervised learning. So this is just a recap of what we have learned so far. So last class, we have seen the motivation for learning machine learning, and we have seen how machine learning has evolved over the years, and we have seen the major differences of what is artificial intelligence and what is machine learning and what is deep learning. And in fact, we have seen some of the real-time applications of machine learning in our day-to-day life. And then we have seen the boom of machine learning right now, why machine learning is in trending right now. And we have seen three major driving factors for that. The first one is big data availability. As nowadays we can see we have lots and lots of data available. And second thing, we have lots of support from hardware as well. As in the recent days, we have a lot of support from GPUs, which are basically graphic processing unit. Graphic processing unit is a powerful computing hardware support, which is much, you can think of it like 10 times much more powerful than a normal central processing unit, CPU. And other important factor for the current trend of machine learning is the advancement of deep learning. And then we have seen some of the course objectives. We have seen what we are going to learn from this course, what are the concepts we are going to cover in this course. And finally, we have seen what you can expect by the end of this course, what you'll be learning by the end of this course. And in this class, this is the outline of my class, what we are going to learn. So basically, first I'm going to introduce what is machine learning, what is supervised learning, and then I'm going to give formal definition for supervised learning, and then some of the types of supervised learning approaches, and followed by classification and regression. And finally, I'm going to explain some of the algorithms and applications of supervised learning. So this is the machine learning terminologies. Going ahead in this course, these are the terms which I'll be using more often. So it is very important to know these terms in detail. So first one is feature vector. Feature vector is basically a compact representation of the data point. As I told before, that machine learning is everything about learning from the data. So when we say learning from data, we have to represent the data. So feature vector is nothing but a compact representation of data point which is specific to the task. Let's say, for example, if you take a same data set, for example, facial images. So from the same data set, we can perform different tasks. Let's say, for example, we can do face recognition, we can do facial expression recognition, where in face recognition, we just have to identify the person. In facial expression recognition, we have to find out the expression of the person, whether he's sad or happy and stuff like that. So depending on the task we are going to do, we have to extract compact representation of the data. And then class label. Class or label is basically the target variable associated with each data point. And then we have training data. Training data is basically the data which is used for generating the training model. And then we have validation data. Validation data is used to validate the training model which we got from training data. And then we have training model. Training model is basically the prediction model which is generated from the training data. And this is the model which we deploy it in real time to predict the label or class of test data. And test data is basically the real-time data which we will be evaluating our training model. And finally, we can be able to analyze the performance of our system, performance of basically our prediction model, using certain measures like accuracy, recall, and precision. So these are the fundamental terminologies in machine learning. So if you see even I mean like any machine learning books or machine learning articles, so these are the terms which you will be seeing more often. So if you have any doubts in this, you can ask me right now also before going ahead for further.
Praveen, so can you give a bit more some detailed example for the feature vector, like in a
Yeah,
way?
sure. Sure, definitely. Yeah, okay. So feature vector is you can think of a feature vector as so we have different data, right? Let's say, for example, we have a data for depending on the domain we are working on. Let's say if you see, you can be working on financial domain, or you can be working on speech signals like Alexa and stuff like that, or it's like you can be working on facial images. So you have different kinds of data set, right? So before so we have to represent the data in some compact representation. All right. So when we learn our machine learning model, when we want to learn the model from the data, it is very important to remove the irrelevant information and to represent the data efficiently with respect to the task we are going to perform.
So
Right.
here the yes. So here the feature vector is like the array of the features.
Yeah, feature vector is basically a one-dimensional vector. You can
Okay.
think of it as like you can think of that as a one-dimensional vector. It's a vector basically,
Okay.
right? So if you have an image, or if you have a speech signal, or even financial data, whatever the data you have, before feeding that to your machine learning model accepts only vectors.
Okay.
Okay, whatever the data, first you have to transform the data into one-dimensional vector.
Okay.
Because if you directly feed the data, it can't accept that. It can't be able to process the data. So if the machine learning model has to learn from the data has to be always represented in terms of vectors, one-dimensional vectors.
Yeah. Okay. Yeah.
So the
Understood.
transformation of, or you can see as a mapping function from your data to one-dimensional vector is feature vector.
Okay. Yeah. Cool. Thank you.
Yeah. So yeah. So yeah. So shall we go ahead? Is it clear? Or okay.
Yeah, Praveen. Like, yeah, it's cool for me. Yeah.
Yeah. Okay. Fine. So we'll go ahead. Yeah. So these are the major types of machine learning approaches. So when I say machine learning, you can classify the entire class of machine learning algorithms into these three major categories, right? So first is supervised learning and unsupervised learning, and finally reinforcement learning. So in this class, we will be focusing on supervised learning, and in the following classes, I'll be explaining even unsupervised and reinforcement learning algorithms as well. Yeah. Yeah. So supervised learning is basically learning from the data, as I told before. So when we think of the way how humans learn from the data, so let's say if you think of a toddler, okay, the way they learn is like we teach them I mean like each object. Let's say if you want to teach them what is an apple, what is a banana, or table, or everything, we uh, we teach them, right? So and then they learn from their experiences. So we human, we learn from their experiences, and then we store the information, right? Similarly, so if we have to mimic that with a computer, okay, we have to feed the data. So basically uh, so if you see in the way the computer it learns is from the data which so which is basically it acts like an experience, right? So in computer, so it learns from the data, and then depending on the application domain. So basically, if you see the focus here is we have to learn from the data, and then we have to learn a predictive model, which is basically target function. Okay, so we have to generate a predictive model from the data, which can be used to predict the values of test data. Okay, so this approach is known as supervised learning. So basically, we have supervised information, supervised data, which is basically we can see like each data point is associated with a label. So that is supervised information. So we use that information, and then we generate the training model, and then we use that model for predicting the test cases. So this is what it is. So if you see here, we have a data. So as I told before, feature vector is nothing but a vector. It's a one-dimensional vector. So if you see here, you can see k attributes here, right? Like a1, a2, and then up to ak. So this represents the feature vector, and each feature vector is associated with a class, right? It is so it has a predefined class, right? So that is your data. So from that information, so from that data, we have to learn a prediction model which can be used to predict the classes of new cases of test cases. So when I say learning, okay, so basically, so if you see the information we have, okay, we have a data set which has supervised information, and then we know the task which we have to perform on top of the data, and then we have certain performance measures, like as I told before, we have like accuracy and precision recall, which is used to analyze the performance of the system. So the computer has to basically learn from dataset D to perform the task so that it learns the predictive model, and finally we can be able to evaluate the performance of the model.
Does that
Yeah,
mean do we specify the same data again and again, or the data changes there? The data set D, because why I'm asking is that if you want to measure the performance, it's done on the same D and T in this supervised learning, or it is like data set is a, it can be different, task also is different, but you can still measure the performance differently.
yeah, that's a good question actually. So the thing is, so in the next slides, I'll be explaining that in detail. But the idea is basically you have to divide the data into train data and test data, okay, validation data. So we learn the training model from training data, okay, but we will be evaluating the performance of the model with validation data. So the data which we use for evaluation is different, and the data which we use for training is different,
Okay.
right? So because normally what we do, normally when we are developing a system, right? Normally when we developing a system for any real-time application, okay, we uh, uh, we capture the data. So so first we capture the data, and then we collect the data. So based on that data set, we generate the model. But ultimately, it has to be, so it has to be evaluated with real-time test data, right? Because if it is not performing well with the real-time data, then we can't use the model, right?
Yeah, got it.
So the evaluation of the model is always with the real-time data, but the predictive model is generated from the training data, which is different from real-time data.
Okay.
Okay. Yeah. So this is the fundamental assumption of learning, and this is a very basic fundamental assumption, right? So the assumption here is every data set will have a distribution, right? if some of you are familiar with statistics and stuff like that, basically if you see a data set, for example, let's take a data set of a simple example where we have to find out the distribution of weights of the students in a class, right? So in that case, let's say if you have 100 students, right? So we want to find out the distribution of weights of the students, right? So we do a bar plot kind of thing. So let's say if you take the range of the weights of the students are like, let's say from 50 to 60, right? We find out the number of students who fall in like 51, 52, 53 and 50 and then up to 60, right? So that will form a distribution. It can be a Gaussian distribution or it will be like a distribution. So the fundamental assumption is the distribution of the training data should always be identical to the distribution of test data, right? If this assumption fails, then no matter how efficient your training model is, it's not going to perform well with test data. So this is the very fundamental assumption which holds for any machine learning algorithm. Okay, but the thing is, in practice, this assumption is often violated because, for example, we can't have that much of data while training itself, because no matter how efficient your training data is, so obviously real-time data is somewhat different from training data. Okay, so there are certain techniques and certain algorithms to handle this kind of approaches and challenges, right? So the thing is to achieve better performance on test data, training examples must be efficiently representative of the test data. So we should be able to cover as much as variation in test data with training examples itself, so that whatever we have in test data, that will fall into the distribution of training data. Yeah, so this is the overall flow of the supervised learning approach, right? So if you see this flow, so basically you have a data set, right? And then the first and foremost thing is we have to do pre-processing on the data. First we have to clean the data. Cleaning the data or pre-processing the data is basically removing the irrelevant information or redundant information from the data for the specific task, right? So for example, if you I have some more examples in the next slides. Maybe if I explain that, it will be easy for you to understand. But pre-processing is basically removing the irrelevant and redundant information, I mean, like in the data. So once you do pre-processing of the data set, we have to split the data set to training data and validation data, right? So typically in most of the cases, training data will be around 80% of your data set, and validation data will be around 20% of your data set. And we have to generate the training model from the training data, okay? And that training model will be the predictive model, which we will be evaluating with the validation data here. If you see we have the training model here, and we will be evaluating the training model with validation data, which will give you a certain score, so that we can be able to measure the performance of the prediction model. And ultimately we can also evaluate the model with another models. So we have lots and lots of algorithms in supervised learning. We can be able to compare different algorithms and evaluate the models as well.
Praveen,
Yeah.
in the previous slide,
Yeah.
so what factors actually that the data is differentiating between the training data and the validation data? Can you give
yeah, actually there is no factor anything of that, sir. You can randomly divide the data as 80% and 20%. So there is no specific strategy that you have to follow.
So for example, like if I have 100 images of an apple,
Okay.
so for example, so I can blindly differentiate the first 80 belongs to the training data, and the next 20 belongs to the validation data.
Yeah, you can do that. So let's say, for example, if you see this example, you have data set of images of cats and dogs, right?
Yeah.
So in this case, let's say if you have 50 images of cats and 50 images of dogs, right?
Mm-hmm.
So in
Yeah.
training data, you you just have to make sure that you have images of all the classes. Okay, so let's say if you so out of 100, if you are taking 80% of the data, you have to take 40 images of cats and 40 images of dogs,
Okay. Mm-hmm.
right? And then for validation data, you have to take 10 images of cats and 10 images of dogs,
Okay.
right?
Mm-hmm.
So the only thing that you have to ensure is you should have all the classes in training data and validation data.
Okay. So this step must be done manually, right?
Yeah, this
So
is
the
done manually. Yeah, this is
okay.
done manually. So
Okay. Cool.
this one you had to do that after pre-processing.
Okay. Yeah. So once
Okay.
the cleaning data is done, so we need to do it manually. So the cleaning data also should be done manually, I guess. Is it right? Or
Yeah, cleaning data. So it depends. So it depends on the domain you are working on, right?
okay.
So there are different pre-processing approaches when you're working with images, or you can be working with speech signals, or you can be working with financial data.
Yeah.
Let's say, for example, if you are working with speech signal, right?
Mm-hmm.
So whenever we speak, there could be a lot of noises in the background. There could
Yes.
be a lot of noise, so we have to suppress those noises. So that is basically pre-processing of speech signals,
Okay.
right? Similarly, if you take images, okay, so if you let's say if you see this example itself, you have an image of a cat here, right? If you
Mm-hmm.
see my cursor
Yeah.
here,
Yeah.
so if you see this image, you have a lot of background information here,
Yeah.
right?
Right. Yeah.
So pre-processing is basically removing those background information, so we don't need that information.
Okay.
So it is something like extra information which we don't want.
So you just take the object in the
Yeah,
image.
we take only the object of this cat information. So we take only
Okay.
this portion of the cat, and then we remove the background. So when I say a pre-processing, it varies with the domain you are working on,
Okay.
right?
Yeah.
So
Right. Yeah.
let's say for example, if you're working on financial data,
Mm-hmm.
right? So in financial data, your noise will be different. So in financial data, maybe you might be having some unnecessary text or some unnecessary words or stuff like that. So let's say if you're dealing with text data, right?
Yeah.
So in text data, let's say if you see stop words like some verbs like is, was, of.
Yeah.
So these are all the words which is not that much important,
Yeah.
right? So we have to remove all those stop words, right? So pre-processing varies with from domain to domain depending on the data you're working on,
Okay. Yeah. Cool. Got it, bro. Thank you.
right? Yeah. So this is an example of classification of cats and dogs, right? So basically, so as I told before, let's say if you assume that we have 50 images of cats and 50 images of dogs, and we want to do uh, and we want to generate a, prediction model which can be able to predict the test image as a cat or dog. So the first thing is we do pre-processing on these images, and then we remove the background information which is irrelevant for our task, and then we extract only the objects, and then we divide the data set into training data and validation data. So we take 40 images of cats and 40 images of dogs as training data, and 10 images of cats and 10 images of dogs as validation data. And then if you see the right hand side image here, this is your training data which you have cats and dogs. So if you see this image, we don't have any background information. we just only have the image of the cats and dogs, right? So this is the training data. So from this training data, we estimate the function f of x. So the function f of x is basically the predictive model. It's basically the training model which we generate from the training data. So there are lots and lots of algorithms to estimate this function f of x, which will be going in detail in the subsequent classes. So if you see here, we have an outline of an image here. We don't know whether it is a cat or dog. So this is the test image. So we feed that image to our prediction model that will give you the prediction, and it will say whether it is a cat or dog. Okay, so this is the outline of the algorithm. So basically we have a training data of cats and dogs. So from this data we generate the function f of x, which is basically the predictive model. So we use this model to predict the test data, and then we assign a class for that. So basically we predict the label of the test data.
So here, Praveen, the test data of, so for example, so on the f of x, we're inputting the test data, right?
Yeah, right.
So for the function f of x, we're inputting the test data. So
Yeah.
if, for example, a image that has a background is going as input to the f of x, like the one you mentioned before.
Even from the test data, okay,
Yeah.
whatever the pre-processing steps and the feature transformation steps you have done for your training data, you have to do the same thing for test data also.
Oh, okay.
Right.
Cool. Yeah.
So as I told before, the predictive function will always takes only one-dimensional vector.
Okay.
Okay. No matter the type of data you are dealing with, it can be image, speech, text, or whatever it can be. But always the a predictive function assumes that input is an one-dimensional vector.
So in real time, so the image has a background, right? So
yeah.
So it will be converted as a one-dimensional vector and then validate it.
Yeah, so in real-time data, first we have to take the test data, and then we have to do pre-processing on the test data, and then we have to extract only the significant information, and then we do apply the same feature transformation which we used for training data, and then we convert that image to a one-dimensional vector, and then we feed that one-dimensional vector for your function f of x.
Okay. Yeah.
Okay, so it is the same procedure. Whatever you follow for training data, we follow the same procedure for test data also. Test data or validation data, whatever it is.
Okay, thank you.
Right? Yeah. So now here, yeah. So this is, if you see this image here, if you see the left-hand side image, so the moment you have this, you convert your dataset into one-dimensional feature vectors. Okay, you can be able to represent these feature vectors as data points in space, right? Because let's say if you take a two-dimensional plot, let's say if you have if you see this plot, you have two features. You have sound and class, right? You have different sounds for cats and dogs and different class for cats and dogs. So similarly, you have lots and lots of features, right? So similarly, you can be able to represent the one-dimensional feature vectors as data points in space. So if you do that, if you represent the data points in space, you can be able to see that all your data points of cats will form one cluster here, and all the data points of dogs will form one cluster here, right? Because depending on the similarities of the objects, because if you see, I mean, like all the cats will be very similar to each other, okay, and similarly all the dogs will be very similar to each other. So when we plot these data points on space, you can see that all these form one cluster, all these data points of cats will form one cluster here, and all these data points of dogs will form one cluster here. Now the question is, if you have a test data, okay, let's say this star symbol is your test data. Now you want to find out whether it belongs to this class or this class, whether it belongs to the class of cats or whether it belongs to the class of dogs, right? So if we have to predict the class of this test data, the first thing is we have to find out a separating hyperplane here. So if you see the right hand side of the image, you have a dotted line, right? Red dotted line. So this red dotted line is basically the function f of x, which is basically the training model or predictive model, which separates the data points of cats from the data points of dogs, right? So if you see here, if you have a separating line here, based on the line, I can be able to see, let's say if this star data point falls somewhere here, I'm sorry, okay, if it falls somewhere here, I can be able to say that it belongs to the class of dogs, right? Let's say if it falls somewhere here, I can be able to say that it belongs to the class of cats, right? So basically we are estimating this plane, this separating line, the separating hyperplane. If you see in terms of high dimensions, it's a hyperplane, right? So basically our function f of x is basically this line. So once you obtain this line, whatever the test data you have, you can be able to say whether it belongs to this side of the line or this side of the line. So that is how we predict the labels of test data. So this is how this is the mechanism of supervised learning algorithm. So till now, if you have any doubts, you can ask before we are going further. Yeah, if we don't have any doubts, then we can go ahead. Yeah, so this is the two major categories of supervised learning, or you can see two major classes of algorithms. The first thing is classification, and second class is regression. Classification is basically the task of mapping the input to output, which will be discrete. Let's say, for example, so in the previous example, we have done classification of cats and dogs. So the test data should belong either to cats or to dogs. So you have only two discrete labels, right? You don't have anything in between, right? So that is classification. So classification is basically classifying the test data into some discrete classes. It can be like cats or dogs or elephants or stuff like that. And regression is basically the task of mapping the function from input to output, where your output is a continuous where your output is so it takes continuous values. For example, if you take, for example, we have to find out the weights of the students in a class, right? So if I say weights of the students, weights can be anything. It can be like starting from so it can take any value in real time value, like 40, 41, 42, 43. So it can take any continuous value in, I mean, like in real value. So basically regression is something which we are predicting continuous values, and classification is something which we are predicting discrete values. So I guess this example will help you to explain to understand better. So basically, if you see the left hand side image, you have an example of classification. So in classification, we are basically trying to do classification of apples and oranges, right? So it's a two class problem. So in classification, as I told before, if you do pre-processing and feature extraction, and finally if you get the one-dimensional feature vectors of your images, you can be able to represent that as data points. And if you plot those data points, you can see that all the data points of apple will form one cluster here, and all the data points of oranges will form one cluster here. And then you have the separating line, which is basically the function f of x. And given a test data, we just need to find out whether it belongs to this class or this class. So it's a two-class problem, which is discrete. But if you see the problem of regression, so you have height versus weight, right? So if you want to find out, the heights of the students, and you wanted to find out a model which can be able to predict the weights of the students in the class. So if I say weights of the students, so it can take any real value. I mean, like in the integer values, in the range of integers, it can be like anything like 40, 50, 60, 70, 80, and it is not discrete, right? It's continuous. So regression is basically we are finding out the model, the function, predictive model f of x, which will give you the the real value output, or you can say, or it's like which can give you continuous value of the output. And we have lots and lots of algorithms in classification, and we have lots and algorithms in regression as well. And these are some of the applications of supervised learning. So if you see, this is the application of face recognition. So this is one of the major application which is being used in many devices as well. So so if you see this application in face recognition, basically first we have to generate a data set of facial images of different persons. Let's say if you see here, we have 4 persons, we have 4 identities. So we first have to gather facial images of with different variations, like of different pose, occlusion, with different lighting conditions, so that we can be able to cover as much as real-time variations. And then we do pre-processing, feature extraction, and then we generate the training model, and then we deploy that in real-time environment, and then we can be able to do face recognition in real-time and real-time settings. And this is another application in financial domain. So let's say if there is a financial institution, so basically the problem is if we have lots and lots of applications, credit card applications, the problem is basically to approve or reject the application, right? So it's a two-class problem. So there are certain factors based on which we approve or reject the application. So there are certain factors like age, marital status, annual salary, outstanding debts, and your credit rating, and these are the factors. So based on these factors, we generate the feature vectors. So this is our data here. So here our data is age, marital status, annual salary, outstanding debts, and credit rating. So based on this data, we generate the feature vectors, and then we find out our model, our prediction model, which will be two-class predictive model. And given a new application based on this data, it can be able to approve or reject the application. And these are some of the algorithms in supervised learning: linear regression, logistic regression, Bayes classifier, support vector machine, and random forest. And these are widely used algorithms in the field of machine learning. So we'll be going through each of these algorithms in detail in the subsequent classes.
So Praveen,
yeah.
So for example, if you go to the previous slide, yes, no, yeah, this one.
Yeah.
So here we're deciding factor. So either side, right? Either approve or not approve.
Yeah, right.
So can this be done with any of the algorithm, or we need to choose a particular algorithm only, like the classification or the regression?
Yeah, right. Yeah, that's a good question. So you have lots of algorithms in classification, and you have lots of algorithms in regression. So these two are entirely different. You can't use a classification algorithm for regression problem, and you can't use regression algorithm for classification problem. It's entirely different, right?
Okay.
So, and it's like different algorithms have different strategies, right? And even if you want to get a better hands-on, you can try different algorithms, different classification algorithms, and you can see which algorithm is performing better for your application. So typically, so it depends on the problem we are working on. So depending on the challenges and depending on the problem setting, we have to choose the algorithm,
Okay.
right? So
Okay. Yeah.
that is something which we can be able to learn when we start uh, working on some machine learning algorithms. So when you start doing some assignments or when you start doing some implementations, then you can be able to understand, I mean, like which algorithm is better for which problem and for which domain. So that is something which you gain from your experience by spending more time and by implementing lots and lots of algorithms.
Okay. Yeah. Cool. Thank you.
Yeah. Yeah, so for example, if you see here, linear regression so it is used mainly for regression problem. You can't use it for classification. And rest of the algorithms are used for classification. Logistic regression is used for classification. Bayes classifier is used for classification. And support determination it's a breakthrough algorithm in 90s. Even in many companies are using support determinations before deep learning, and it is like widely used algorithm. And you have random forest, it's again a classification algorithm. So the next concept will be linear regression, which we'll be learning in our next class. And I guess before that, in the next class, we'll be learning some hands-on implementations with Python in the next week. And yeah, thank you so much for your time, and if you have any questions